Hello, welcome to everyone in this video. This is our lecture number 7. Already 6 lectures are covered. You know, in lecture 1 we discuss about the singularity point of differential equation. Then lecture 2 3 consist the Frobenius method. Then lecture 4 the legendary differential equation is polynomial generating function, etc. Lecture 5 consists the Bessel differential equation and Bessel function, etc. Lecture 6 consists the Hermite polynomial differential equation and its generating function, recurrence relation, etc. We discuss in this last 6 lectures, right? So if you want to watch the previous 6 lecture, you can go through the description box, link are given there. In this lecture, we want to discuss about the application of this differential equation, mainly Legendre polynomial differential equation, that is consistently lecture 4, and then the Bessel's differential equation. We want to discuss the application of these two cases. Okay, so first one, you can watch the syllabus of this physics on a third semester, University of Calcutta. In the first lecture we cover up this portion, and the second and third one this one, and fourth, fifth, sixth consist this one, except these two application, that is multiple expansion of electrostatics and the array disk diffraction, Fraunhofer diffraction through the circular aperture. These two application actually want to discuss in this lecture. Clear? This is all the syllabus. I think you all know about the multiple expansion in electrostatic. In the previous semester, you already discussed about the multiple expansion of the electrostatics, and this formula was derived in the another process in the binomial theorem expansion. But we can use the Legendre polynomial to solve this multiple expansion in electrostatics. Okay, so just check out, if this is a charge distribution and we wants to find out the potential at the field at this point P. Okay, so at this point P, the potential will be like that, where rho is the charge density, which is function of r prime. R prime is the source point, and this is the field point. This is the origin. You can write here, that is this is the source, and this is origin, and this is the field point, right? Field point, this is the 3 point. So this 1 by r minus r vector, that is this distance must be this distance. So this distance must be r vector minus r prime vector. So the magnitude of this vector will be like that. We can write down this one with respect to this. So just multiply, you can get this relation, the angle between these two r and r vector taken as gamma, so this will be cos gamma. Okay, so look at this expression. I think in the previous lecture, that is lecture 4, you know this expression is well known expression. This is the Legendre generating function of Legendre polynomial. I think you know about the generating function of Legendre polynomial. If you watch the previous lecture number 4, you know about this. This is the nothing but the generating function of this Legendre polynomial, right? So just compare these two equation and just put this value. You can say this is the Legendre polynomial expression like that. Now this potential will be like that, and then compare these two things. You can easily write down this in terms of Legendre polynomial. Now we can easily find out this potential monopole term, dipole term, quadrupole term, all can be find out by this Legendre polynomial expression. So this is the beauty of this Legendre polynomial expression or Legendre polynomial, such that we can you can find out this multiple expansion very easily. Just we think remember this single formula. Using this single formula, we can and if you know the Legendre polynomials, I think you can find out the Legendre polynomials by Lorentz formula. So using these two relation, you can find out any order of this multiple expansion. Here we just find out the monopole, dipole and quadrupole. You can get octopole, and higher order also can be derived from this equation. This is the beauty of this Legendre polynomial. Okay, so this is the application of Legendre polynomial, and comes into the another application of Bessel's, that is the Bessel differential equation, as has the application of the Fraunhofer diffraction through a circular aperture. I think this also covered the previous semester. that is in the physical optics, that is Fraunhofer diffraction already discussed. You know, in a this is an open space. For that there will be a screen, and there is a superposition of this light comes from this aperture will be arising there, and this mathematical expression you can just check. I think I just want to say you that is the intensity appears at this region is depend only this Bessel differential equation. You can see this differential equation, this integration will be matches I think these matches will be Bessel differential equation. This expression is very clumsy, but I want to finalize say that this expression, that is the final intensity expression, depends on the Bessel differential equation. So if you express this physical problem in this polynomial, that is the Legendre or Bessel or Hermite polynomial, then it will be easier to remember and they calculating the higher order, right? So that's why we study this thing, special things, that is Legendre differential equation, Bessel differential equation, or Hermite differential equation. Okay, and if you wants to see the array within this diffraction pattern, the linear scale this will be like that, and the logarithmic scale this will be increased, and the actual image will be like that, because in the linear only this is the prominent and this is very low intensity, so there will be negligible, but in the logarithmic scale you can see there will be a prominent, because this will be appears. Okay, so I think you clear about the fact that is polynomial, legendary polynomial or Bessel function actually used in various application. These are the two application which are included in our syllabus, that's why we discuss here, but there are various application for the these three differential equations in the upcoming semester or the higher studies. You can watch this application, this differential equation will be very much application. So so just watch the previous three lectures to understand this polynomial expression, and just remember this recurrence relation. Since this recurrence relation used very much here, you can if you remember this previous lecture, the Bessel's equation, this recurrence relation also derived here. We just use here. I think you can do this expression. This is very long calculation, that's why I do not want to waste time to express this calculation, but just I want to say the main funda of this lecture is that to understand what are the applications of this legendary Bessel and Hermite polynomial distribution. So that's it for today, and this is a supplementary graph. Actually in this lecture 6 I do not express that is the zeros of the Bessel's function. Here you can the tabular form, you can see these zeros are Bessel's function as and this is not a symmetrical interval, this is not a symmetrical interval. I just draw in this lecture that is in the positive part, but also in the negative part this is the symmetry. Okay, so this is the part of the lecture number 5, that is the Bessel differential equation. Clear? So that's it for today. This is all about me. This is my contact details, and you can connect with me this with the Telegram channel and also Telegram group in the same name, Physics by Laxmikanta sir, and this is my other platform. And this is my YouTube channel details. Go to this channel, you will get the different physics related video, and like this session if you learn something from this video. Share this video to your friends, either he or she also get benefit from this video. Subscribe this channel if you new in this channel, those already subscribed. Thanks for subscribing. Press the bell icon to get that notification of upcoming video. In the upcoming video want to start the solution of the partial differential equation with the separation of variables. So stay connected for the next upcoming video. Thank you. We'll be meet in the next video as soon as possible. Thank you.